All right, that is going. Okay, maybe before we jump right into this, recap about what we were talking about. You remember the topological property we've been talking about for this past chapter? Connectedness. Good guess. Connectedness. Do we have any vague notion of what it means for a set to be connected?
Yeah, it means that if you have it means it's not disconnected. And disconnected means you have two, you can split it into two sets where they do not have common elements.
Two disjoint open sets.
Yes.
Two disjoint non-empty open sets. Yeah, a lot of technical little pieces, but yeah, the big notion is a set is disconnected if I can split it into two open sets. Partition it into two open sets. Otherwise, it's called connected. Yeah. Okay, so we're going to be going over a notion today called path connectedness. Path connectedness is a stronger notion than connectedness. For a set to be, for a topological space to be path connected, means it's connected and then some. It gives us more structure. It's like, if I tell you that you got an A, that's a stronger notion than you passed a class. If you got an A, you for sure passed the class. If you passed the class, it does not mean you got an A. Similarly, if you're path connected, you're connected. But if you're connected, it does not mean that you're path connected. You could be, you might not be. And we'll look at a couple spaces, a couple of topological spaces to show the difference, although fortunately we don't get proof of any of them. So, high level notion, what does it mean for a topological space to be path connected? It means I can draw a path between any 2 points in the space you choose. Pick any 2 points in the space and I can take my pencil and I can draw a line to the next point without picking up my pencil, staying inside the set. That's what it means to be path connected, roughly speaking. That's intuition for it. So, before we get into the exact definition of path connectedness, I want to go back to the exact definition of a path because I'm sure that we've forgotten it, what exactly it was. So let's go back, this is back in chapter 4 when we defined what a path was. So let's recover that exact definition, make sure it makes sense. So let X be a topological space and let 0 to 1, this closed interval, be a subset of R. What I meant by that, I finished it. Let that be a subset of R, be a subspace of R, where R has a standard topology. So we're talking about this subspace with the standard topology that inherits from R. Make sense so far?
Yeah.
Okay, so then we define a function, f, from this space to x. This function is called a path in x, provided f is continuous. So f is a function from 0, 1 to x, and it's continuous. And it starts at f of 0, and it ends at f of 1.
So there's only maps to like two elements?
No, this is a closed interval. It's all the numbers between 0 and 1.
Oh.
We're mapping everything in this interval to some points inside of x. So x might be over here. If this is a path inside of x, and when we map it, it's going to start at some point, and it's going to go something like that and end at some point. It's going to give us a path in x. Make sense?
Mm-hmm.
So that's going back to what a path is.
And continuous is 1 to 1 and non-2?
No. Pre-image of open sets are open.
Okay, that's what I see.
Continuous. Not a bijection, not 1 to 1, not 1 to 2.
Well, I was just wondering, if you define it that way, can't one of those points go to more than one
Yeah.
point in there? Then why saying it's continuous makes so it looks like that?
I can do the constant function. That maps everything to x. You're used to working with constant functions. Look at the function f of x is equal to 2. That's a constant function, right? So something similar here. I'm mapping from here to here where I map this whole line interval to that point. Then that could be a path from that point to that point. Stays at the point the whole time. Nothing wrong with that.
Okay.
Can this function, can one of the points in the domain map to two things? Can one left-hand element have two different right-hand elements?
Can one left? No, because that's not a function.
Okay.
But a right-hand element can come from multiple left-hand elements. It's perfectly fine. Any other questions before we continue about paths? Okay, so now let's go over what it means for a topology to be path connected, and now you can basically guess it. A topological space X is path connected provided that for any 2 points in X you choose, there exists a path from P to Q in X. There exists some path connecting them. When we say a path from P to Q, we mean P is the start point of the path. This is what f of 0 goes to. And Q is the end point of the path. This is what f of 1 goes to. So in our picture here, before how I had it, if this is 0 and this is 1, then this is f of 0 or P, and this is f of 1 or Q. P, Q, or over here next. Does that make sense?
Yeah.
Okay. So connected provided that for any 2 points you choose, there exists a path from the first to the second in X. A subset A of X is called path connected in X, provided that the subspace topology induced on A is path connected. If it feels like I didn't really say anything more, that's because I basically didn't. And we define notions like this over and over and over again.
You're just saying A is path connected in X as long as A is path connected.
With the topology it inherits from X. So how do I check if A is path connected in X? So this was talking about the whole topological space, X, right? Now I'm saying, what if I want to talk about just a subset of X and talk about it being path connected? How do we check that? We give it the subspace topology and see if it's path connected. That's all we're saying.
Okay.
So it's just because it's very convenient to be able to say, let A be connected in X. So we need to define exactly what that notion means, even though you could have already guessed what it means just based off of what you were given. Okay, so we feel like we got the notion of connected, not connected,
Path connected.
path connected.
Yeah.
Good? Pretty straightforward one. Okay, so let's prove now that path connectedness is a stronger notion than connectedness. From here on out, I have to write connectedness 100 times, so I'm just going to use CONN for connected. All right. So what are we going to prove? We're going to prove path connected spaces are connected. If it's path connected, it's connected. So let X tau be a path connected topological space, and let XY be 2 points in X. Now, maybe before we go over this proof, we're going to have to make reference to something that we're talking about again. You remember that when we had a connected topological space, sorry, not when we had a connected topological space. For any topological space, we could break it down into its components. You remember talking about components? They're the biggest connected subsets that you could possibly make. So if we're talking about in R2, for a second, so in R2, looking at a subset in R2, is we take this open set right here and this open set right here. Those are two very different open sets, right?
Mm-hmm.
This is disconnected. I create an open set containing this and an open set containing this, no problem. So this disconnected topological space has two components though, because each of these components are connected.
You're saying those are components?
Okay, let's try this one more time. We'll give like this. Here's A. Notice it's split in two as a subset of R2. A is a subset of R2, and you'll notice it's split into two components.
Yes.
Notice that just this set right here, we'll call just this half of A, we'll also call it B, and just this half of A, we'll also call it C. Notice that B is connected in A, and C is connected in A.
Yeah.
Notice that any subset of B, not any subset, but I can also take smaller pieces of B. I could have just taken this, and that space by itself is also connected. So it's like the biggest connected subset I can get. with the points over here, and the biggest connected subset I can get over here are what we mean by components.
Okay.
And the set has to be disconnected for there to be more than one component.
Correct. The set's connected if it only has one component. Okay. Helpful notion that we had is, to help us define our component, we said that if I can find two connected sets, so I know that this set is connected and I know that this set is connected. If I can find two connected sets that have any overlap, then their union is also connected. You remember that theorem? And it kind of makes sense. If this point's connected to this point and this point's connected to this point, then this point's connected to this point. Maybe you remember we also came up with our connected relation is connected. 2 points are connected if you can put them in the same connected set. And we talked about how it's an equivalence relation. Is that ringing some bells?
Yeah.
So we use the equivalence classes of that equivalence relation to define a component. And it all hinged on the idea that if two connected sets have any overlap, then their union is connected. And so you keep unioning up all the connected sets that in any way contain points in here, and it just like balloons out to the biggest possible connected set you can get, right? Okay. So that was components. So we're going to need to make reference to some of the ideas that we proved there in this next proof. So path connected spaces are connected. So let X now be a path connected topological space, and let little x, little y be any 2 points in big X. Our job is to show that little x, little y are in the same component. If for any 2 points in big X you choose, they're in the same component, then big X only has one component.
Yeah.
And therefore, it's connected. That's going to be our thinking here.
Okay.
So ultimately, I need to show that little x and little y are in the same component. That's what we're after. Okay. So, now remember what I know. I know it's path connected, and I'm trying to prove connected. So since little x and little y are 2 points in there, then there exists a path between those 2 points. Right?
Mm-hmm.
So then there exists P, some path from 0, 1 to x, such that P is a path from x to y. Nothing weird there? Okay. Since P, notice that a path has to be continuous. So since P is continuous, and since the closed interval 0, 1 is connected, then the image of 0, 1 is connected in X.
Yeah.
So our path is a continuous function from a connected set. So its image has to be connected.
So the path has to
Back to our definition of a path. Maybe we should have re-talked about this closed interval is connected in the real numbers. Hopefully that's already intuitive.
Oh, it makes sense.
The closed interval 0 to 1, this is connected in the real numbers. Does that make sense that this is connected?
Mm-hmm. We went over that.
Yeah, we did. So we know that this is connected. We know that continuous functions preserve connectedness. You remember that proof? So this is connected. Continuous functions preserve connectedness. A path is a continuous function. Therefore, a path always preserves connectedness.
Yes.
Okay.
So the image of every path has to be connected.
Yes.
So the image for our path P of 0, 1 has to be connected in X. You with me so far?
Mm-hmm.
Okay. Therefore, any 2 points in X are in the same component. Right? I found a connected set, namely the image of P, that contains both those points. So they're in the same component. So any 2 points you choose are in the same component. Therefore, X is connected. You follow the logic there?
Yeah.
It all hinges on the idea that this set's connected and continuous functions preserve connectedness. Good?
Mm-hmm.
Cool. Okay, so now let's go over one that is connected but not path connected. And I was going to prove it, but the proof is absolutely massive, and the payoff isn't that great. Like, it doesn't give you any great intuition for continuing topology, so I decided not to prove it, but we'll just talk about it.
Okay.
The proof is in the book that none of you have, so if you want to take a picture of the proof, that's fine, before you leave in my book. Anyways, first one we'll talk about is the Topologist Whirlpool. Now, first off, polar coordinates. Are we all okay with polar coordinates?
No.
No. Okay, coordinates. There's two ways to get the coordinates. There's two ways to talk about where a point is. Coordinates are just saying where a point is, right?
Mm-hmm.
So once I pick my origin, I can start telling you where all the points are. If you know that my units are meters or something like that, then I can tell you, Peter, you know that this is my origin. If I tell you I want you to go to the point 3, 1, you know I'm saying go 3 units in my x direction, and then 1 unit in my y direction, so you know I'm talking about this point. So you can think about Cartesian coordinates are telling you how to get from the origin to the point you're talking about. You go this far in the x direction, this far in the y direction, that's how you get there. The point 3, 1 is going 3 in the x, 1 in the y, right? Notice that there's another way that I could get to that point 3, 1. Rather than going 3 in the x, 1 in the y, I could just point directly at the point, turn some angle, call it theta, and then I could walk some distance, call it r. And that's another way to get to the same exact point. Does that make sense?
Okay.
So polar coordinates, rather than listing the x and then the y, we list the angle and then how far to walk. The theta and the r. But we actually do the r then the theta. Because I don't know why. It's terrible that we do it that way.
Okay.
So, that's what this is. Your r and your theta. Your angle and how far you walk that way.
Okay.
So let's plug in some numbers to get a feel for it. If you're not comfortable with polar coordinates, you probably don't like radians either, huh?
Radians.
Okay. We'll redraw this image using degrees because it doesn't matter. You can also do it with degrees, it's just going to take longer to spiral out. So, erase. I need to keep S1, but we'll erase all that. Oops. Let's see why it's erasing. So right here's just S1, right? The circle.
Mm-hmm.
And now we'll plot this set using degrees. So theta is just degrees. And we're going from 0 degrees to infinitely many degrees. Notice that once you go past 360, you just keep going around the circle.
Yeah.
Right?
I don't see that.
So here's 0 degrees, right?
Okay.
This is 90 degrees,
Mm-hmm.
180, 270, 360. Right?
Yeah.
450, 630, 720.
Okay.
Did I mess up?
I don't know.
I must have, because 720 is right here. I added 9 months. Accidentally added 18 months. But you get the point, right? If I tell you to turn 360 degrees, that's turning a full circle. If I tell you to turn 720 degrees, that's turning a full circle twice, etc. So if I tell you to turn infinitely many degrees, that's saying spin forever. Right?
Okay.
So we're going to spin forever, marking out this distance each time. So first, in the direction, you know that this is where we start measuring degrees from, right? 0 degrees is this way. So 0 degrees is pointing this way. And what do you get when you plug 0 into this?
I actually can't read that fraction, that's kind of see.
Theta over theta plus 1.
Theta, okay.
So it's going to approach 1 as theta gets arbitrarily big.
Right.
Which, I didn't mark this off, but this right here is a circle with radius 1.
Okay.
Oh, okay.
1. Okay, anyways. So, when I plug 0 into this for theta, what do I get? I get 0, comma 0. That means go 0 in the 0 degree direction. Okay, that's right here. Now, we don't actually include that point because you notice that we don't quite use 0, but if I use a number really close to 0, then I'm still really close to 0. Alright, let's try another one. let's see what do we get when we plug in something like 5 degrees. If I plug in 5 degrees, what do I get? I get, in the direction of 5 degrees, I need to go 5 over 6, right? This is 1. If I went clear to here, that would have been 1, but I'm only supposed to go 5, 6 in the 5 degrees direction, which is roughly right there. So my function starts right here, and it's jumping clear out like that, right?
Mm-hmm.
And then if we go into 6 degrees, I need to go out 6/7. And if I go at 8 degrees, I need to go out 8/9 or whatever. And so it's going to spiral out like this really quick. Notice by the time I get to 90 degrees, what do I need to, how far up do I go? 90 over 91. So by the time I got 90 degrees, I'm basically right there. So this spiral comes around. Sorry, it should be way closer to the circle. Right there, we're at 90 over 91. By the time we get clear over here, we're at 180 over 181, which is really, really close to 1. And so this instantly spirals really close to the edge of the circle. And you see how it's going to get closer and closer?
Mm-hmm.
Like if you plug in 10,000 degrees, who knows where that lands? Let's pick another one. Let's pick 36,000 degrees. Okay, that's a multiple of 360, so that's going to be right here. And notice that that's going to be 36,000 over 36,001, which is absurdly close to 1, right? So this spiral is getting closer and closer to S1. We can't even draw it because it gets close so fast. But notice that it never actually reaches S1. So this set A never actually reaches the boundary. It just gets really, 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 really close.
So it's never, there isn't a pathway between 2 points.
Yeah, so this never reaches S1. Now, the whirlpool that we're talking about, the topologist whirlpool is A, this spiral, union S1. You with me? So the spiral gets really, 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 really close to S1, but never actually quite gets there, and then we're unioning it with S1. Okay, these two together give us a topological space, give us a connected space that isn't path connected. Now, hopefully the path connected is appealing to your intuition, in that since A never quite reaches S1, then we can't draw a path from A to S1. There's no way to do it.
S1 is just the boundary of that circle, right?
That's one way to think about it, yeah. The boundary of the spiral.
So why is it
Kind of weird because we have exact terminology for boundary, which
I get what
I
you're
don't know. The spiral is its own boundary in R2, but
saying.
the way that you're saying it, the way that you're thinking about it, yes.
Right.
So how is it connected then?
How is it connected? Okay, so remember what it means for it to not be connected. It means that we can split it into 2 open sets.
But we can't. 'Cause
But we can't, because there isn't any open set that we can get that gets us all of A that doesn't also. Here's a way to say it. Any open set containing some of S1 is also going to contain some of A. Right?
Mm-hmm.
And so there's no way to split this into 2 sets, because anytime I get some of S1, I get some of A. I don't know how else to say that.
That makes sense.
And S1's connected, so if we get some of S1, we have to get all of S1. So then we have to somehow be able to split A into 2, which A by itself is going to be connected. S1 by itself is going to be connected. There's one way to think about it. S1 by itself is connected. A1 by itself is, or A by itself is connected. So both these are connected. And any open set containing some of this has to contain some of that.
So it's connected?
Yeah.
Okay.
Because what does it mean for it to be connected? In order for it to be disconnected, I'd have to be able to find open sets to split it, right?
Mm-hmm.
But any open set containing some of this has to contain some of this, and those are both connected pieces. Now that's not a proof. The proof of this is very involved. I'm just trying to give you intuition. Okay. So this is one example of a space that's connected, but not path connected. The other one we call the topologist sine curve. And now I'm just realizing if you're not comfortable with radians and you're not comfortable with polar coordinates, probably not comfortable with trig functions,
Yeah.
like the sine function.
A third of us are.
Huh?
I said a third of us are.
A third. That's not a majority. No. Okay. If you don't know what the sine function is and explain this, I don't think it's worth it. Well, we can help Anna make sense of it real quick. Obviously, the sine function, as x gets smaller and smaller, has its oscillations more and more rapidly, right? So notice we're not polar coordinates anymore.
Right.
We're just x and sine of 1 over x. Now sine of 1 over x, for smaller and smaller values we plug in for x, is a bigger and bigger angle we plug in here.
Right. Okay.
Okay, yeah, so small change in x gives us big change in what we're taking the sine of, so it oscillates faster and faster and faster.
Yes.
So we get faster and faster oscillations between -1 and 1, really, really fast, as we approach this, I. I is the interval -1 to 1, but just in the y direction. So we've got the sine approaching 0, obviously never using 0, because then we're undefined. Notice that A never actually intersects I, but I, once again, is just like the boundary of what this sine curve is approaching.
Yeah.
And that there's no way, once again, to draw any open set containing some of this I without getting some of the sine function. Okay. And you guys got the whirlpool. That's enough. You got to feel for what happens in these weird spaces where you have connected but not path connected. Weird stuff's going on. Typically, if you have one, you have both.
So is that one both connected and path connected?
This one?
Yeah.
No. This is another example of a similar thing happening, where you've got something getting closer and closer but never quite getting there, but getting closer and closer everywhere. Notice the spiral is getting closer and closer to this point. It's also getting closer and closer to this point. Pick any point on S1, and A gets arbitrarily close to that point. Right? That's what makes, so I can't draw any little ball containing some of S1 that doesn't get some of A.
So why is it not path connected?
Because A never actually intersects S1.
Okay.
It gets arbitrarily close. Pick any distance you want, it gets closer than that distance. You say, I want to get within 0.001 of each other. Yep, they do. And they do everywhere. This point gets within 0.001 of A. This point does, this point does. Any point on S1 does. So think about S1 using that Emma's vernacular of the boundary of it. If we think about S1 as the boundary of A was the spiral part, right? So A spirals out, getting closer and closer and closer to S1 everywhere, but never quite reaching it. Similar thing happens with this function, even if you don't know what it's doing. What it's doing is oscillating up and down between 1 and -1, faster and faster and faster, never actually reaching this line segment between -1 and 1. It's just getting closer and closer and closer to it. And it's getting closer and closer to it everywhere. So this back and forth sine wave going up and down as it approaches here. So it starts like this, and then it oscillates faster and faster and faster, getting closer and closer to this line segment, but never quite getting there. But it gets closer and closer to it everywhere. It gets closer and closer to this point on the line segment, this point, this point, this point, any point you pick on the line segment, the whole sine function gets arbitrarily close to it. So that's going to be a property that you see of these weird spaces that are connected but not path connected. So it's very contrived to see them, to have them come up. I think. I don't know. Maybe there's some other natural way, but it's just not pictorially nice. So we don't go over it. Anyways, okay, so there's two examples of showing spaces that are path connected, or are connected but not path connected. Okay. Now let's move on. If X is path connected and F is continuous, then the image of F is path connected. Or in other words, continuous functions preserve path connectedness. We know they preserve connectedness. They also preserve path connectedness is what we're going to prove. Make sense? what we're trying to do? Alright, so let f from x to y be continuous where x, the domain, topological space, obviously x and y are topological spaces since we're talking about continuous function. Let x and y be topological spaces and f is a continuous function where x is path connected. Our job is to prove that f of x is path connected in y. Notice that f of x might not be all of y. It could only be some of it. Right? So we're not proving that all of y is path connected. We're proving that the image of x is path connected. Notice that if f is a bijection, or is a homeomorphism, then y would also be path connected. Because then f is 1 to 1 and on 2, and so it uses up all of y. And so then we know that y would be path connected as well. If it was a homeomorphism. But we don't need a homeomorphism. That's a lot more search than we need. All we need is f to just be continuous, and turns out that's enough.
Okay.
So path connectedness is a topological property. If two topological spaces are homeomorphic to each other, then they're either both path connected or they're both not path connected. Okay, so let f from x to y be continuous and assume that the domain topological space x is path connected. I'm trying to prove its image, f of x, is also path connected. So pick 2 points out of there, p and q. I need to find a path from p to q. And then we're done. Pick any 2 points in there you want. If I can find a path that connects those 2 points, then f of x is path connected. So let p and q be any 2 points in the image of x, and let little x be the preimage of p, and little y be the preimage of q. Now notice that I'm saying in there instead of equal to it, because there might have been multiple points that map to p. I just need one of them. There might have been multiple points that map to q. I just need one of them. So that's why I'm using that in notation instead of equals. Because all we know is that this function is continuous. We don't know that this function is one-to-one. So the preimage of a point could be multiple points. With me so far? Okay, so now we have x and y are 2 points in big X, right?
Yeah.
So since x and y are 2 points in big X, then there's a path connecting them. Because big X is path connected.
Right.
So, since x is path connected, then there exists some path, call it g, from 0, 1 to big X, from little x to little y. Some path in x connecting little x and little y. Or from little x to little y. Okay. The important property that maybe you forgot, so let's restate it. The composition of continuous functions is continuous. We're going to be using that, obviously. Observe that f composed with g, f after g, is now a function from 0, 1 to y.
Yeah.
Because g maps 0, 1 to x, f maps x to y, so when you compose them together, you now have from 0, 1 to y. And notice that f is continuous by assumption. Let f be continuous. And g is continuous by definition of a path.
Connectedness.
Okay, so we're composing 2 continuous functions together, so the result's continuous. And observe that, what is f composed with g at 0? F composed with g at 0 is the same thing as f of g of 0, right?
Mm-hmm.
What is g of 0?
X.
That's just x. Remember that g is a path from x to y. So g of 0 is x, it starts at x, and it ends at y.
Oh, little
So
x.
f of g of 0, yes, thank you. This is little x, not big x. Good point.
Okay.
F of g of 0 is the same thing as f of little x, and f of little x is p. Because x is in the preimage of p.
Mhm.
So,
Is it equal to p?
yes, equal to p.
Why? Why?
If x is in the preimage of p, this is all the points that map to p.
X is in the preimage of p.
The preimage of p is all the points that map to p.
Okay.
So if a and b are in the preimage of p, then f of a equals p, and f of b equals p.
Okay, yeah.
In either case, f of x equals p. Perfect. And exact same thinking for f composed with g at 1. That's f of g of 1 is little y, f of y is q. So notice that f composed with g is a function, is a continuous function from 0, 1 to y that starts at p and ends at q.
Yeah.
Therefore, it's a path from p to q. Therefore, f composed with g is a path from p to q. Therefore, y is path connected.
No. Therefore, f of x is path connected.
Thank you. F of g is a path in y. Therefore, f of big X. Good catch. That's a big X. We'll make it tall but skinny. F of x is path connected. Anyway. Wonderful.
So y isn't path connected, but f of x is.
Correct.
Y might be path connected, but we don't know.
Correct.
Okay.
If it just so, because if f of x is equal to y, then y is path connected. If our function happens to be on 2, then y is also path connected.
Okay.
Wonderful. Okay, definition. Now, remember before that we did our, I think we did our tilde with a sub c, and x tilde sub c y was the same thing as saying x and y are in the same component. Okay, we're going to define the similar thing, except for we're going to say x and y are path connected. So definition, given some topological space x and 2 points little x, little y, and big X, then we're going to say x is related to y using this relation tilde p. I'm just going to read it as related because it's the only relation we're talking about for the next little bit. X is related to y provided that there exists a path in big X from little x to little y. Make sense?
Yeah.
Okay, so now let's, we're not going to prove it, but we'll go over to make sure you feel like you could easily prove it if you had to, that this thing is an equivalence relation. Okay? So first off, is little x always related to little x?
Yeah.
Yeah. What's the function?
Just be from x.
F of t equals x. Just map the whole number line to just that point. There you go. That's a path from that point to that point.
Right.
How do I know that this function is continuous?
Because the image of one sets are open.
We proved, especially for functions that are constants, that constant functions are continuous. The function is a constant is continuous. So this is a constant function. It might not look constant to you because you're used to viewing x as a variable. Maybe I should have said x naught related to x naught and made that an x naught. Because t is our variable here, right? For any t you pick between 0 and 1, just map it to that x naught, whatever that x naught is.
Yeah.
Okay, there is a function from x naught to x naught. Continuous function from x naught to x naught. Whose domain is that? Therefore, yes, x naught is related to x naught.
I think I get the point behind your x naught, but can you go over that a bit? Like, why do you say x naught?
Typically, you use x naught to reference a particular number, whereas x is a variable.
So x is like any number you can pick.
So when you're used to seeing something like f of x equals x squared, then you know that that represents an infinite number of points satisfying a relation.
Yeah.
But then if I say f of x naught is equal to x naught squared, that's usually referencing a particular point.
Okay.
So we would have marked out, we would have said, here's f of x's function. Now for some x naught, let's look at its output. There's no reason that one's right and one's wrong. It's just a matter of convention to help you not get confused.
Gotcha.
So usually it's, if we're using an x, we are hinting, hey, we're talking about a variable. And if we put a subscript there, we're saying, hey, remember this isn't a variable, it's a constant. We just don't know what the constant is. That's all it is. So, every point x naught is related to itself. Right? With the constant function. Okay, next. So that's reflexive. Now we need to show symmetric. We need to show that if x is related to y, then y is related to x. Right?
Yeah.
Yeah.
just showing its equivalence relation, just need to show the three properties. Reflexive, symmetric, transitive. So if x is related to y, does that imply y is related to x? I don't know, let's see. So if x is related to y, what does that mean? That means that there exists some path, f from 0 on to x, there exists some path from x to y. That's what it means for x to be related to y, right?
Yeah.
Now, since x is related to y, well then there exists this path. So then I'll define some new function g from 0, 1 to x by g of t is equal to f of 1 minus t. Notice when you plug in 0 for g, what do you get?
1.
1.
F of 1, right? Is that what you mean?
Yeah.
Plug in 0 to g, we get f of 1 minus 0 is f of 1. F of 1 is y.
Mm-hmm.
So when I plug in 0, I get y. When I plug in 1, I get f of 0 is x. So g now is a function from y to x. It's a map from y to x. Last thing we need to justify is g continuous.
Yeah.
How do you know g is continuous?
Because it has a path,
And it's
right?
going from that integral to a topological space.
Because g is defined completely in terms of f is a continuous function.
What?
G of t is equal to f of 1 minus t.
So?
Okay, 1 minus t, is that continuous?
Yeah.
Okay, yeah, it's polynomial, right?
Yeah.
Okay, so a continuous function inside of a continuous function is a composition of continuous functions. So g is continuous. That's another way that we can look at it. So g is a continuous function from 0, 1 to x that starts at y and ends at x. So it's a path from y to x. So x being related to y does imply y is related to x. Follow that?
Yeah.
Okay. Now we need to prove transitivity. We need to show that if x is related to y and y is related to z, then then x is related to z. That's what we need to show. So we know that x is related to y and y is related to z. What does that give me? That gives me that there exists some path f from x to y, and there exists a path g from y to z.
Mm-hmm.
This is a terrible spot to have to move my phone. Maybe actually we can still get
You'll
most likely.
probably get
Yeah.
a lot of the chalkboard.
Yeah, okay, we can still see all that. Okay. Anyways. So since x is related to y and y is related to z, then I have these two paths, f, a path from x to y, and g, a path from y to z. Right? So now I need to create a path from x to z. Well, here's my path. Then h of t is going to be equal to f of 2t when t is between 0 and 1/2, and h of t is going to be equal to g of 2t minus 1 when x is between 1/2, or when t is between 1/2 and 1. So notice, we're just like stretching our interval. It's kind of like instead of using the interval 0 to 1, we're kind of cheating and using the interval 0 to 2, using this function for the first half and this function for the second half. That's kind of what we're doing. So notice, for 0 to 1/2, we're going through f, but now we're going through it twice as fast as we were before. So what you used to get when you plug in 1/2 to f, you now get when you plug in 1/4 to h. H of 1/4 is equal to f of 1/2.
Okay.
H of 0 is still f of 0. But now h of 1/4 is equal to f of 1/2, and by the time you get to h of 1/2, you get f of 1. So now, as we go from 0 to 1/2 in h, we go through all of f. You see that?
Yeah.
Okay. Similarly, this 2t minus 1 is going to do a similar thing for 1/2 to 1. So now notice that going from 1/2 to 1 in H is the same thing as going through all of G. So H of 1/2, looking at this bottom one now, H of 1/2, what do we get when we plug 1/2 into here?
0.
No.
What's
0.
2 times 1/2?
1.
Minus 1. So that's G of 0. And notice when we plug in H of 1, what do we get?
1.
G of 1.
G of 1.
And then for any point in between, obviously we get something in between, right?
Mhm.
So, is it appealing to your intuition what this function is doing now? From 0 to 1/2, it goes through all of F, and then from 1/2 to 1, it goes through all of G.
Okay.
Okay, now there's one weird thing going on here, and that is that we're using 1/2 both up here and down here. So, the question is H of 1/2 equal to G of 0, or is H of 1/2 equal to F of 1? We said H of 1/2 equals G of 0. We also said H of 1/2 is equal to F of 1. Which one is it?
They're both the same.
They're both the same. What is G of 0? That's where the pad G starts. Where does G start?
Where F ends.
But where does it start? We know the exact point where it starts.
Why?
Y. G is a path from Y to Z.
Yeah.
So what is G of 0?
Why?
Y. So this is Y. What's F of 1?
Why?
Y. So those are both the same point. So we're using something called the pasting lemma. This is going way, way back. If I have two continuous functions that overlap, and where they overlap, they give the exact same value, then hooking the functions together still gives you a continuous function.
That makes sense.
Yeah.
Okay, so now let's go over my actual explanation now that I think you have a high level understanding of everything I said. And this will probably just be repeating, who knows. Okay, so then H of t equal to this is a path from X to Z. Note that H of 0 is equal to F of 0 is equal to X, and H of 1 is equal to G of 2 minus 1 is equal to Z. And since H of 1/2 is equal to F of 1 is equal to G of 1 minus 1, or G of 0 is equal to Y, then H is continuous by the pasting lemma. So H is a function from X to Z, and it's continuous.
Yeah.
So it's path. So we have X is related to Z. So we now know that X is related to Z. Good? Feel like that's something that you could rigorously prove on your own now, if you had to?
Perhaps.
What was weird?
Given the motivation.
Is it just coming up with these functions that seems
Yeah,
like,
that-
how would I
that's-
ever do that? Okay. I guess that kind of makes sense. That seems weird the first couple times you see it. I vaguely remember. But as you get used to them, it wouldn't have been that hard for you to come up with it as you see a couple of these. Because you're just doubling the domain and then cutting it in half. That's all you're doing here. Notice you have the 2t and the 2t, but you only want this to count for the second half. So you minus a half, but you doubled it, so now you minus 1. It doesn't seem that strange, but I get why that can seem like a bit much at first. Anyways, so we proved that this thing is an equivalence relation, and equivalence relations give us
Equivalence classes.
equivalence classes. So we can partition up this set X now into these equivalence classes. The equivalence classes of this relation are called the path components of X. So we have the components of X, now we have the path components of X. Good? Now you'll have tons of homework problems, doing cool things with those,
Yeah, but
Sounds cool.
and that's the end of compactness. Not compactness, connectedness. Alright, so that finishes the last section for chapter 6, and now we're starting our last chapter, chapter 7.
This is our last chapter.
Yes,
Next week going to be our last class.
week after.
Week after.
Yeah, so for the summer class, so our last class is going to be the 10th. at the start of that class is when we'll decide what we're doing the following week. So I'm imagining people who are going to be interested in saying what class they want me to do are going to show up at first. We'll quickly talk about that, take our vote, whatever. And then we'll do our last topology class, and then that way next week I know what I'm teaching before class starts, which is nice. Okay, anyways, yeah, so hopefully, maybe this will take way longer to get through than I think. Compactness. So compactness is the last topological property that we're going to talk about, and this is the one, more than anything, where when we talk about intuition for what it is, and then when we go to its actual definition, there is just no connection. Those are just very different things, and compactness is something that took a long time for us to develop topologically. I mean, the definition of compactness, it's not even 100 years old yet. So we're talking about math that was developed within the past 100 years, which is very strange for a math class, right?
Yeah.
So, very unintuitive, but we'll go over it. So try to establish some intuition first. Let's look at some sets. So this is all in R2. Obviously we're going to use R2 to try and establish our intuition. We're looking at this rectangle containing all the points inside and its boundary. We're looking at the circle, S1. Doesn't have the inside, doesn't have the outside, just a circle. We're looking at these points. And now we're looking at, we've got a rectangle, and now we're filling in just lines. We're filling in the line at, so this is a rectangle from 0 to 1. Its height is, who cares? But it's going from 0 to 1, and we put a line at 1/2, we put a line at 1/4, 1/8, 1/16, 1/32, 1/64, etc., putting these lines in.
And so you're not filling in the middle, you're just doing
Not
it
filling in the middle, just solid lines.
Okay.
All these sets up here are compact. These sets down here are not compact.
I mean, the ones on the
In
bottom.
R2, it turns out compactness is going to be bounded, closed sets. You might remember from calculus the sequential compactness theorem, which had to do with closed bounded intervals on the real line. Compact intervals on the real line, or compact sets in R1 topology, standard topology on R1. So, compactness.
So, you know the donut, if you were to make the inside of the donut...
If that was solid, it'd be compact.
Okay, gotcha.
You'll notice all the compact sets are closed, and they don't go off to infinity.
How are
That's
the
the
points
intuition.
compact?
They're closed. Get rid of those points, and what do you have? You have R2 with just some random holes in it. Right?
Oh yeah, but that's...
Which is open. So, just those points have to be closed. Okay. So, closed bounded sets intuitively are going to be compact. Closed and bounded.
But that's not the definition.
No, that is not the definition.
Sad.
That's just the intuition. Might have been the definition at one point. It's the definition in calculus. Because it turns out that's what compact sets are there, but bounded is kind of a weird notion when you don't have the real numbers. I don't know if we have a notion of bounded in topology in general. Doesn't make sense to me. Because topology, you don't necessarily have distances. Okay, so our first definition. We need to define three notions before we even go to the definition of compactness. Three notions of covers. So given some topological space X, let A be a subset of X, and let O, don't get confused by what this O is, let O be a subset of the power set of X. What is in O? Subsets of X. It's a collection of subsets of X. Collection, so keep in your mind this is always a collection of sets. O, a collection of sets. Subsets of X. The topological space that we're talking about. So A is some subset of X. O is a collection of subsets of X. With me so far?
Yeah.
Okay, O is the thing we're going to be interested in. O is said to be a cover of A, provided that A is a subset of the union of O. In other words, take all the sets in O, union them together. If that gave you A, if A is a subset of that union, then O covers A.
Okay.
Pictorially, we think something like this. Here's my A, right? And if this is a set in O, and this is a set in O, and this is a set in O, notice that they cover A when you take the union of those three sets.
Yeah.
That's what we mean by a cover. It's pretty intuitive. So O is said to be a cover of A, provided that A is a subset of the union of the sets in O. If all the sets in O taken together cover A. Feel like you got that one?
Yeah.
It's very important that you understand each of these very well, because it's all we're going to be talking about over and over again this whole chapter, is these covers. Okay. Next. O is said to be an open cover of A if all the sets in O are open sets. Or in other words, provided O is a cover and O is a subset of tau. So if O is a cover and all the sets in there are open sets, then it's called an open cover.
Open cover. Okay.
Yep, so we got a cover, now we've got an open cover. Alright, good so far?
Yeah.
Last one, a subcover. Oh, I want you to draw a picture of an open cover real quick. So here's X, here's some set A in here. Now taking that open ball, union that open ball, union that open ball, union that open ball would be an open cover. So if O is a collection of those four open balls, can you see my open balls okay?
Mm-hmm.
Yeah.
Then that would be an open cover of A. Good? Okay, last thing. If O covers A, and O prime is a subset of O, such that O prime also covers A, then O prime is a subcover of O.
Okay.
So in other words, notice that O, pretend I also had this open ball, and I also had this open ball, and I also had this open ball. Notice I could get three of the three open balls I just added, and I would still have a cover. So that would be a subcover of the new cover I've drawn up here. The new cover I've drawn up here is now composed of, what is there, 6 balls? I can get rid of 3 of them and still have a cover. Oh no, 7.
Yeah.
So there's 7 up there, I can get rid of 3 of them and still have a cover. So that would be a subcover. Alright, so we've got a cover of A, an open cover of A, and then once we have a cover of A subcover of A. Good?
Yeah.
Alright. Here comes the definition. Okay, our topological space, X, is said to be compact, provided that every open cover of X has a finite subcover.
That's a weird definition.
It is very weird. So we've got X.
They can
The
have
whole
an
topological
infinite
space.
subcover?
Yeah, there's tons of infinite covers and there's tons of infinite subcovers. If I have an infinite cover, then it itself is an infinite subcover, because every cover is a subcover of itself. Right?
Mm-hmm.
But furthermore, let's jump to an example, then go back up to the definition, because I think that this will really help. So we're going to look at O equal to the closed interval, -3 to -1, -2 to 0, -1 to 1, 0 to 2, 1 to 3. It's just these intervals. The intervals that I've listed here, I drew pictures of them down here. -2 to 0, that's -2 not including -2, to 0 not including 0. So this one is right here. -1 to 1, I drew that one right here. 0 to 2, I drew that one right here. 1 to 3, I drew that one right here. You see the picture so far? And then obviously there would be another one that went right there, and there would be another one that went right there, another one that went right there, another one that went right there. Goes off our picture. You with me so far?
Yeah.
Yeah.
Okay. Notice that all these sets, all these intervals, are a cover of R. They cover all the real numbers. pick any real number you want, it's going to be in one of those intervals, right? It's going to be in one of these intervals. You with me?
Mm-hmm.
Now notice that if I get rid of one of them, doesn't matter which one, but randomly get rid of one. Let's get rid of negative 1 to 1. So let's say I get rid of that one. Then, that would be also getting rid of this one. And notice now that we don't have 0. 0 is no longer covered by this set. So O no longer covers R.
Wait, R is not compact?
That's what we're showing. R is not compact. Here is a cover of R, right? If I remove a single set from this, then it's no longer covered. Correct?
Mm-hmm.
Yeah.
So, O for sure does not have a finite subcover. O is infinite,
Because it doesn't even.
and
have
if I
a
get rid of even one of these elements, it's no longer covered.
Yeah.
So this definitely does not have a finite subcover. You with me?
Yeah, it doesn't
Okay.
even have
So
one.
R is not connected. So let's read this again. Topological space is said to be, I said connected, compact. Don't let me say connected. Compact. We're done with connected. Forever. Now we're talking about compact.
Forever.
Forever. Okay. So our topological space is said to be compact, provided that every open cover, any possible open cover you can find. Here's one.
That covers all of X, is what you're saying.
Yes. It's every open cover of X has a finite subcover. R is not compact because here is an open cover of R. All those sets are open and it covers all of R. But it for sure does not have a finite subcover.
Right.
Feel like you're getting this a little?
Yeah.
A little, but the
It's very awkward.
yeah.
So let's talk about another one. This one I didn't write out because I want you guys to think, huh?
I have a question. If R is not compact, then how is things in R cross R? Well, is R cross R compact then?
Is R cross R compact?
No. Okay, I see now.
No, and R closed bounded subsets are what you can pretty much think for is going to be compact intuitively. Okay, so let's think about another topological space to help our intuition. So let Xt be any topological space where X is finite. Question, is that topological space compact?
Think so.
You think so? Why do you think so?
Because it has finite
Should be.
elements.
It has finitely many elements. Keep going.
Yes, it's compact.
How do you know it's compact?
Okay, if you have an open set enclosing all of it, and the open set has that finite, it has the X in it, and X is finite, so X could just be the subcover. Can the subcover just be X?
We're not saying we can find a subcover. We're saying that for any open cover you choose, I can now eliminate sets till I'm left with just a finite subcover. Notice that going back to R by itself is a cover of R, and it's a finite cover of R.
Okay, but does a subcover have to cover all of X?
Yes. Otherwise it's not a subcover.
That's what I'm saying. You take an open set that covers X, you remove everything except X, and all you're left with is X.
How do you know X is in there?
Because
R-
it's a cover.
Look, this covers R, but R was not in there.
Okay.
You with me?
Yeah.
So this is good. Keep thinking out loud through this. I think you're working through some of your
R not in
misconceptions.
there though?
Yeah, she's 10 times further than that.
Because isn't it R in and of itself that it's covering?
This covers R. If I
So
union
would
all
R
those,
be in it?
R is not in this set. What are the elements in this set? The interval -2 to 0. That's in there. -1 to 1. That's
Yeah,
in
but
there.
if you union all of them, isn't it R?
If you union all of them, it gives you R. That doesn't mean R is in there,
Oh, yeah, okay. That makes sense.
right? Yeah, none of those are R. R is not an element of that set. All the elements of that set look like A R is definitely not in here. Okay. So back to this one. I know that X is finite,
Yes. That's it.
and that's it. So how can I argue that X is compact?
You can't.
I need to prove that every cover has a finite subcover. So 1,
Okay, but every
Let
subcover
O
has to
be
cover the whole
a
thing.
open cover of X. Okay, got you started. If O is an open cover of X, what do I know about O?
Has open
Wait,
subsets
that's
of X.
yeah.
It has open subsets of X. What are the open subsets of X?
Oh.
The whole set X.
X is one of those, but I don't know that X is in there.
X isn't in there, but
The
it's
open-
the finite set is the subcovers.
The open sets of X are just X and then just it?
We don't know that. We have no clue what the topology is on it.
Oh, right. Then it's just the open sets.
Let's see, where were we defining these things?
You
Alright,
have to
let's
have
go
a
back and look at
finite
this.
amount of subcovers.
Given some topological space, let A be a subset of X and let O be a subset of the power set of X. So it's a collection of subsets of X. So what do we know about this O?
It's a collection of subsets of X.
So, or another way to say it is it's a subset of the power set of X.
Yes.
Mm-hmm.
Okay, wonderful. So 2. Then O is a subset of the power set of X. But notice that the size of the power set of X is less than or equal to what?
Oh. I forgot what was it,
XN.
but I know you.
You have what?
XN. I don't know.
Oh my wow. 2 to the n.
Oh.
Oh!
Oh.
Oh! Clear back to basic discrete math.
Yeah.
Okay. If I have an n element set,
Mhm.
how many subsets can I create from it? 2 to the n. How do you justify that? For each element in there, so I'm creating some subset, how many ways can I do that? Well, notice I have 2 to the n choices that I need to make. I need to choose, am I going to take this one, yes or no? That's 2 choices. Either I take this or I don't. Now I need to decide, am I going to take this or not? 2 choices. So 2 to the n plus 1 because I start at 0. 0 to n instead of 1 to n.
Okay.
So I need to make 2 to the n plus 1 decisions. So there are 2 to the n plus 1 possible subsets of that thing. Right? So
Okay.
the size of the power set of X is equal to 2 to the n plus 1. I don't know why I said less than or equal to. And I know that O is a subset of this thing. So then, the size of O is less than or equal to 2 to the n plus 1, which is definitely finite. It's its own finite subcover.
Is that not what Emma was getting at?
Wow.
Well, she wanted to argue that it, well,
It's not.
no. Because her argument kept using that, referencing the X. We have no clue what's in that O. All we know is it's an open cover. We have no clue what our topology is. But we know that by definition, topology is a subset of the power set of X. And so since this is a subset of tau, and tau is a subset of the power set of X, this is a subset of the power of X, since it's an open cover.
And you show that's finite because X has a finite number of elements.
This is a collection of subsets of X.
Mhm.
There are this many possible subsets of X. This can have at most this many elements.
Okay.
It might have less, but it can have at most this many elements. Is that a finite number or is that infinity?
It's fine.
It's finite. So, it's finite. Not too bad, right?
That's an example.
That was an example.
They're supposed to be easier.
Well, no, you're supposed to struggle with them all the way through. Hopefully you struggle the entire time, growing a little bit each time. If it's all easy, you're not learning anything.
They're supposed to be easier than the theorems.
Probably are.
Yeah, let's do some theorems now.
Look at that lemma.
Move the camera.
My word.
Yeah, what a lemma.
I like the theorem after it. It's just
Yeah.
2.
Let's see. We can just stick this right here and be fine. Oh, I might have to steal you. Sorry, that's gonna bug me. Well, I had it. Can you see? Where's that? Yeah. Okay, good enough. All right. Continuing. I guess another definition. Let x tau be a topological space. Let A be a subset of X. Oh, then A is compact in X, provided that A is compact with the, or in the subspace topology inherited from X. So exactly what we were talking about earlier with a set being path connected in X. A is path connected in X if when you give it the subspace topology, it's path connected. Similarly, A is compact in X if when you give it the subspace topology, it's compact. Make sense? We know what it means for a topological space to be compact. We've got that definition. Now we're saying some subset is compact if when you give it the subspace topology, it's compact.
Okay.
Feel like I'm just saying the same thing twice? Then you're good. That's what it should feel like. Okay. Now, a lemma, where it's going to feel like I'm saying the same thing over and over again, but slightly different. So let's go over it. So let X be some topological space and let A be a subset of X. Then A is compact in X if and only if every open cover O of A in X has a finite subcover.
That's the definition
Almost.
Oh, compact in X.
Yes. So A is compact in X. In other words, when you give A the subspace topology that it inherits from X, it's compact. If and only if every open cover of A in X has a finite subcover. So we're going to go back and forth between talking about open sets in X and open sets in A. That's what we're going to be doing, back and forth, back and forth. If I can find open sets in A, if I can find a finite subcover of A, if for any open cover in A, I can find a finite subcover of it, then it's also going to be the case that for any open cover of A in X, so using open sets in X now, I can find a finite subcover of it. So if I can cover it with open sets in A, I can do it with open sets in X, and vice versa. That's what we're proving, basically. Do you remember what open sets in A look like?
Just open sets in A.
What?
Open
We're
sets.
using subspace topology, so what does a...
It's an intersection between
Open
X
sets in X.
and A.
Perfect. It's an intersection between open sets in X with the set A. That's an open set in A.
Yeah.
Okay, so that's what we're going to go back and forth talking about. Open sets in X versus open sets in A. Open sets in X versus open sets in X intersected with A. And we're going to switch back and forth talking about those a lot, so let me know if I ever say confusing. Okay, so let's get started. Assume A is compact in X. You need to be careful to put everything here so we don't lose track of what we're saying. Assume A is compact in X. In other words, assume that when I give A the topology it inherits from X, it's a compact topological space. And let O be a subset of tau such that O covers A. The elements of O are the open sets in X. This O is not containing open sets in A. Keep track of what we're trying to do here. I already know that A is compact. I am trying to show that I can find I'm trying to show that for any open cover in X of A, it has a finite subcover.
But don't we already know that by definition?
No. I know that for any open cover of A, in A, it has a finite subcover.
Oh.
That's what it means for A to be compact in X. Yes. So right now, I am assuming that for any open cover of A in A, it has a finite subcover. I need to use that to prove for any open cover of A in X, it has a finite subcover.
In
So-
X or in A?
In X.
No, I'm saying it has a finite subcover in X.
In X. Yes. So I already know for any open cover in A, it has a finite subcover in A. I need to use that to prove that for any open cover in X, it also has a finite subcover in X.
Okay.
Every open cover has a finite subcover. Since my open cover is in X, my finite subcover also has to be in X, otherwise it's not subcovered. Okay, so assume that A is compact in X, assume that for every open cover in A of A, it has a finite subcover, and let O be any open cover in X, or O be a subset of tau. Tau are the open sets in X, right? Such that O covers A. So assume that O is an open cover of A in X. That's all we're saying about O so far. Good?
Okay.
Okay. Now let O prime equal U intersected with A, where U is in O. So I'm taking all the elements of O, and I'm intersecting them with A, and sticking them in O prime. What's O prime? It's taking all the open sets in O and intersecting them with A. That's what O prime is. Am I stressing that too much? So now O prime is a collection of open sets in A.
Yeah.
Wonderful.
I see that.
So let O prime be taking all the open sets in X and intersecting with A. So let O prime this set, and observe that O prime is an open cover of A in A.
Yeah.
You want to explain that a bit more?
Okay, I know that O covers A. If I union everything in O together, that for sure covers A. Right?
Yeah.
Okay. O prime is taking everything in O and just intersecting it with A. So now for every set in O, I'm saying I'm just going to take the elements out of U that are in A.
So it still covers.
So it's still going to cover A, since O covers A. And since O prime is just intersecting each of those sets with A, then O prime still has to cover A. Because we're for sure keeping all the elements that were in A. You with me?
Yeah.
Okay, so you're good that O prime covers A, and you're good that all the elements of O prime are open sets in A.
Mm-hmm.
So then, O prime is an open cover of A in A. It's an open cover of A, and it's using open sets in A. Not open sets in X, open sets in A. That's an open set in A, not necessarily an open set in X.
Okay.
Good? Okay. So now, since O prime is an open cover in A, we know by assumption that it has a finite subcover.
Right.
Because A is compact. What does that mean? That means every open cover of A in A has a finite subcover. This is an open cover of A in A, so it has a finite subcover. And we'll call it U1 intersect A, U2 intersect A, U all the way up to UN intersect A. Some finite number of elements out of this thing right there. You with me?
The reason we call it U1 intersect A is because those are open sets in A, but in order to be open sets in A, they have to be open sets in X intersected with A.
They're open sets and O.
I'm picking elements out of here. I'm picking finitely many things out of here and sticking them in here. I'm just
Oh,
labeling them
okay.
1, 2, etc.
Okay, I see.
Because remember, it's a subcover. So here's our cover. Now I'm creating a subcover from this. I'm picking finitely many things out of here. And here they are, right here. Good?
Mhm.
Now, this is a finite subcover of A. In other words, for sure, A is a subset of the union of this thing. Right?
Mm-hmm.
Then, A is for sure a subset of the union of this thing. Because all we did was made all those sets bigger.
Right.
There we go. So here we have, these sets are now open in X. We have sets that are open in X. And notice that since they're the same U's that we used here are the same U's that we used here, are the same U's that we used in O. Sorry, all those U's initially came from O. Then every single one of these U's, U1, U2, all the way to UN, were in O. So this set is a subset of O. So this is a subcover of O. It still covers A. It's a subset of this, and it's finite. So it's a finite subcover of O. So we did it. We grabbed an arbitrary open cover of A, and we found a finite subcover. Good?
Yeah.
That's pretty much what you do over and over again. So, let's do it again. Now this time we're going to assume that for every open cover of A in X, sorry, I said that right. I said that wrong. Assume every open cover of A in X has a finite subcover. And now we're going to use this to prove that A is compact in X. So what am I going to do? I'm going to grab now a random open cover of A in A and show it has a finite subcover in A. So I'm going to start with, I'm assuming every open cover of A in X has a finite subcover this time. And I'm using that to show that every open cover of A in A also has a finite subcover in A. Inverse of what we just did. Am I losing you?
No.
Okay, so let's do it. Let O prime be any open cover of A in A. The reason I'm using O prime is just because we used O prime to reference an open cover of A in A up here. So try and help continuity there. So let O prime be any open cover of A in A. And observe that for every open set V in O prime, then there must exist some open set U in X such that V is equal to A intersect U. What does it mean to be an open set in A? It means you're an open set in X intersected with A.
Right.
That's the definition of a subspace topology, right?
Yeah.
Okay, that's all we're saying here. I'm saying for every open set in O prime, remember O prime is an open cover of A in A. So O prime is a bunch of open sets in A that also cover A. So each of those open sets can be expressed as U intersect A, where U is open in X, or where U is in our initial topology we're talking about, the topology on X. With me? Okay. Then, we're now going to find O. O is going to equal all those U's. That's all I'm saying. For each V, find the associated U, stick it in O. That's all I'm saying. Now we'll read it out rigorously. Let O equal all the U's where U is in tau, and there exists a V in O prime such that V is equal to U intersect A.
Right.
So U is an open set in X, and it's the open set such that when you intersect it with A, you get V. With me?
I think so.
Okay. Then O is an open cover of A in X, right? We took everything in O prime and we just made the sets bigger.
Yeah.
So if O prime covered A, then O for sure covers A.
Mm-hmm.
So then O prime is an open cover of A in X. And so, by assumption, has a finite subcover, U1, U2, UN. And then, since that is going to be still a cover of A, then when we take all those elements and we intersect them with A, it's still going to be a cover of A. And when we intersect all those with A, we now have open sets in A instead of open sets in X. So that's going to be a finite subcover of A in A now. Here's a finite subcover of A in X. Here's our finite subcover of A in A.
I see.
Okay. I mean, this is really, the logic that we're using here is pretty straightforward. I know it looks like a big proof, but the logic is really straightforward. We're just going back and forth between one topological space and the other. Feel like you got it?
Yeah.
Make sense? That's a yes. All right. So let's move on then. Example. Oh, cool example. So we're going to do A is equal to, let's first look at this set. The set 1 over n for every positive integer, what does that set look like? 1 over 1, then 1 over 2, then 1 over 3, then 1 over 4. And I did that wrong when I drew it down here, so I'm missing 1 over 3, which is going to be between them. 1 over 3 somewhere over here, then 1 over 4, then 1 over 5. Okay, we're in trouble. I can't fit them all. 1 over 6, 1 over 7, 1 over 8, 1 over 9. Da da da. Anyways, you see what the set's doing?
Yeah, it's getting close to 0.
It's getting closer and closer to 0. Never quite gets to 0 though, right?
Yeah.
And it's just points. These aren't intervals, these are just points. Right? Okay. So now we're taking that set and we're unioning it with the set containing 0.
Right.
And we're calling that A. And we're going to show that set A is compact.
How do you union something getting infinitely close to 0 with 0?
This is a set. It has infinite elements, but it's still a set.
Okay.
Now we're saying also put the point 0 in there.
Wouldn't that just be the interval from 0 to 1?
No, we don't have, for example, what's between 1/3 and 1/2? We don't have this point in there. We don't have this point. We don't have this point. We don't have all the points between 1/3 and 1/2 in there.
Oh.
Gotcha.
It's just the points. We have 1, that point. We have 1/2, that point. We have 1/3, and we have 1/4. So the gap between points is getting smaller, 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 but we never have an interval.
So you can have like infinite elements in A, but still have a finite subcover?
Yeah, that's what we're going to show. We're going to show now that for any open cover you have, it has to have a finite subcover. Every open cover has a finite subcover. In other words, no matter how clever you get trying to come up with infinitely many intervals covering this thing, I can always just easily find a subcover of it.
Okay.
Let me show you how easy it is. Oh, it's right here. As you can see, not very many lines. Now, we'll prove this, no problem. So, but I just want to make sure you understand what the set A is, and that's appealing to your intuition. It's these points, getting denser and denser and denser as we approach 0, obviously never approaching 0, and then we manually stick 0 in there as well. Good? That's what we're showing is compact. Alright. Let big O be any open cover of A. So we know nothing about it. I'm going to now find a finite subcover of O. That's my job. So let O be any open cover of A. And observe that there must be some open set in there containing 0. Right? O is a collection of open sets that covers A.
Yeah.
One of those open sets, whatever it looked like, had to have 0 in it. Otherwise it wouldn't be covering A.
Right.
You with me?
Mm-hmm.
Okay. So there must exist some open set in there covering 0. Oh, 0 must be in some open set. Now if 0 is in an open set, and we're talking about the standard topology on R, it must also be in a basis element, So 0 must be in a basis element where the basis element is a subset of U. So in other words, U might have been this interval union this interval. We're saying there had to have been just one interval that 0 was in. Some basis element containing it. You with me?
Mm-hmm.
Okay, that's all we're saying so far. So since 0 is in some open set, then there must have been some piece of the open set, some basis element that's a subset of the open set, such as 0 is in that basis element. Now notice if 0 is in A to B, B has to be a positive number. I can't have zeros in the interval A to B where B is negative. Make sense?
Mm-hmm.
Alright, so since B is some positive number, then by the Archimedean property, there must exist some integer, however big, some positive integer m, such that 1 over m is smaller than b. Does that make sense? No matter how teeny tiny of a number you choose, I can always find an integer so massive so that 1 over that integer is even smaller than the teeny tiny number you chose. Make sense? Okay. So, whatever that b is, I'm guaranteed that there is some positive integer such that 1 over that integer is smaller than b. Which means, since 1 over n is always positive between 0 and b, or since 1 over n is always positive, then that means 1 over n is in U for all n greater than or equal to n. So if n is a natural number greater than or equal to m, I'm too used to doing this in calculus, I probably am losing Utah in the background, so let's write this out a little better. I know that for all n greater than or equal to n, 1 over little n is less than 1 over big M is less than b. For all n greater than or equal to m. Or greater than is what we said there. Notice, if I make, so m is just some big number like 100, right? If I make m bigger, it makes the whole fraction smaller. Does that make sense?
Yeah.
Okay, so that's what we're saying here. So I'm saying 1 over 100, so if n is 100, then I'm saying 1 over 101, 1 over 102, 1 over 103, etc., on forever, are all going to be less than 1 over m.
Yeah.
And 1 over m is less than b. So all those 1 over n's are going to be in this interval, 0 or a to b.
Yes.
You see that? Because 0's in there, and they're always going to be between 0 and b.
Oh.
You see it now?
Yeah.
And since this is a subset of u, 0, u sub 0, I named this one, then they're all in u sub 0. You with me?
Yeah.
Okay, so notice that we just took care of infinitely many points, and we just have finitely many more points to deal with. Right? So now we just have the first 100 points to deal with if big M is 100. We need to deal with 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, all the way to 1 over 100. We just really showed that from 1 over 101 onwards, this set U sub 0 contains them. Okay. So, then for each of those other 100 points, for each point 1 over little m in here, I'm just using 1 over little m as an incrementing variable to talk about each of those points, there has to be some open set in O containing that point. Right? This was stuff we were talking about before. Don't let that confuse you for this line of logic. So for each point in there, there had to be some open set containing it. So then, u sub 0 containing 0 and infinitely many points, and then u sub 1, u sub 2, all the way up to u sub m containing the other 100 points, is finite. And it contains all the points. It's a finite subcover. So the whole trick to this problem is that no matter what open cover you choose to cover this set, you had to pick some open interval that contained 0, right? You had to pick some open interval that contained 0, and whatever that open interval is, you just barely took care of infinitely many points for me.
So now.
And so only finitely many points, maybe it's 100, maybe it's 1,000, but only finitely many points aren't going to be in that interval. So this interval takes care of infinitely many. Now I have m other points I need to take care of. So I know that there's some open set that contains that, so we'll grab that one. I know that there's some open set that contains that, so we'll grab that one. So I'll grab 1,000 other open sets. It might have been redundant. I probably could have made it smaller, but I just need a finite number. It doesn't matter if I use 20 trillion. I just need to find some finite number. Make sense? So we got finite subcover.
How does that make it a finite subcover? Sorry.
All the points from here, all these points right here are in use of 0, right? Now remember that we started out with an open cover. When you secretly chose an open cover, I don't know anything about it. Okay? You have some open cover. It's my job to find a finite subcover of it, right? Now I'm telling you, look inside your set, and one of those sets, I don't know which one, had to have 0 in it, right? Yeah. And it had to have a subset that was an interval containing 0, right? So you have some, I'm calling that set u sub 0. I know nothing about that set except for this interval was in there. Maybe it had some other points over here. Who knows? Who cares? The point is, these points are for sure in that one set, right? Now I say you for sure have a set containing a point 1, right?
Yeah.
So give me that set. You for sure have a set containing a point 1/2, right? So give me that set. And 1/3, and 1/4, and 1/5, and 1/6, and 1/7, and 1/8, all the way up to 1 over 100. So you give me those 100 sets, plus the first set we talked about. Those cover everything.
Okay.
Does that make sense? Cool.
I did have one question. If you remove 0 from A, is it just
Uh,
not compact anymore?
it's not going to be compact anymore.
It seems like you can do the same thing now.
No, because you no longer had to have 0 in there. We don't get to get to that example on this today. We will see an example of this next week. What it has to do with, I'll give you intuition for it right now, is unioning up. So I may come up with an open cover of 0 to 1 like this. So I'm going to show you that this thing is not compact.
Okay.
And you see how this is close to that same idea if we get rid of 0?
Right.
Because it's got the same problem.
Yeah.
Yeah. So here's the cover I can give you of this set. And the cover I'm going to give you of this set is 1 over n to 2 for all n. There's my open cover. Now notice you're in trouble because you have to use infinitely many.
I see.
So that's the counter and why the 0 is important. Good question. Okay. Any other questions? All right. So let's move on to whatever I've written here. Let X be a topological space. Oh, these are 2 proofs that we're not going to do. We're just going to state them, and then we'll move on to other proofs.
Oh. Is it because they're too complicated?
It's because the author said these are an exercise, and it's an exercise that I happened not to do when I went through the class, and I already had so much to write on the board
Alright.
that I thought, yeah, I'm just not going to bother.
Okay.
Okay, so let Xt be a topological space. If C1, C2 to Cn are all compacted X, so is their finite union. And you see that this is true for closed sets. Compact sets and closed sets in terms of R are very closely related, right? So if C1, we already know that a finite union of closed sets is still closed. This is just saying a finite union of compact sets is still compact. That's what this one's saying. This one, special case if it's Hausdorff. If X is Hausdorff, then the arbitrary intersection of compact sets is still compact. So we knew that the arbitrary intersection of closed sets is still closed. The arbitrary intersection of compact sets is still compact, only if our space now is Hausdorff.
So is compactness a property of Hausdorff?
No, they're two separate topological properties. Topological space can be connected, or can be compact. Topological space can be Hausdorff. It can be both. So I kind of think about properties a number might have. A number can be even, a number can be prime, a number can be both. And just because it's even doesn't necessarily mean it's not prime. Just because it's prime doesn't necessarily mean it's not even. It's kind of a bad example because they only have an overlap of 2, but I think you get the point. And yeah, I want to stress the similarities between compact sets and closed sets. Because as I've already told you tons of times, in the real numbers, our compact sets are going to be our closed bounded sets. And notice that the real numbers are a Hausdorff set, so it doesn't disturb us too much that this is only true in a Hausdorff set. And we better remember what Hausdorff is, now we've gone over it 50 times.
Yeah, it's Hausdorff.
For any 2 points, there's this neighborhood around each, and then those neighborhoods don't intersect.
Yeah, any 2 points have their own neighborhood.
Yeah.
Yep.
Mm-hmm.
Alright?
Yep.
They're housed off from each other. They're more than housed off, they're neighborhooded off. Right? Not even their own houses. I'm sure there's some sort of plate joke you could plug in there. Okay. I had a chemistry teacher at MCC, and since he knew it was a play community, he came up with all sorts of jokes to help you get concepts. Like one of them was when you have 2 electrons in an orbital, you can only have one up one and one down one, right? Because when you have 2 wives, you got to keep one upstairs and one downstairs, and that's all you can have. Funny guy. And stuck. Sometimes the jokes work. Okay, next here. If f from x to y is continuous and a is a subset of x, a as a subset of x is compact in x, then f of a is compact in y. In other words, continuous functions preserve compactness. Now notice that f just being continuous is a much weaker notion than a homeomorphism. Obviously a homeomorphism preserves compactness, because we've been saying that compactness is a topological property. Topological properties are properties preserved by homeomorphisms. They're ways that we can distinguish 2 topologies from each other. If one has a property and one doesn't, they're for sure different topologies. They're not in any, they can't be homeomorphic to each other. Okay, so let's prove this one. Where are we? Right here. So let f be continuous and assume that a is compact in x. Let O be any open cover of f of a in y. We need to show that we can find a finite subcover of f of a in y.
Okay.
And if we can, then f of a is compact. Okay, so since f is continuous, then for any open set U inside of our cover, V equal to the preimage of U is going to be open in X. How do I know that?
Because it's continuous.
Because F is continuous. The preimage of open sets are open. So, and I'm going to let O prime be the set of all those V's, where V is the preimage of U, where U is something in O. With me?
Yeah.
So O prime is a collection of open sets in X. O is a collection of open sets in Y. Right? Okay. Now,
And is O prime basically the pre-image of O?
it's the set of preimages. So now, notice that since O was a cover for A
And Y.
in Y, thank you. Since O was a cover of F of A, and O prime is the preimage of O, kind of, then O prime is going to also be a cover of A.
In
Furthermore, it's an open cover of A in X. Yeah. So since O was an open cover of F of A, then its preimage O prime has to be a cover of A. Down here we're talking about an X. All right. Now we already know that X is compact. Or sorry, we know that A is compact in X.
Oh,
That's what I meant to say. So since A is compact in X, then what does that mean? Using our theorem, our lemma over here, we don't have to reference the open sets in A. We can now reference just the open sets in X. That's why that lemma is so useful. So we don't have to go through the headache of thinking about A as a subspace anymore. We can just view it as a subset of X and find open sets in X that cover it. So that's why we went through all that headache. Is so that we can now think about this exactly how our intuition wants us to. So then O prime is an open cover of A, which means that now there exists some finite subcover. So that means that there exists V1, V2 up to Vn, such that it is a finite subcover of O prime. Good?
Subcover of O prime or of A?
A subcover only makes sense in reference to cover.
Oh.
So notice that O prime is an open cover of A. Now, this is a subcover of O prime, which means it's a subset of O prime that still covers whatever O prime covered. Okay, so this is a finite subcover of O prime. So then, the image of this now, so since this still covers A, then the image of all this covers the image of A. So we're going to call the image of V1, U1. The image of V2, U2. The image of Vn, Un. So since all these sets together, when you union them together, you for sure get A. Then when you union their image together, you for sure get A's image. And the image of each of those is open, and there's finitely many of them. So now, that is a finite subcover of O. Notice since we were always using the same sets, these U's that we talked about here were ultimately elements of O. That's important.
Yes.
So we started out with O, we look at its preimage to get our V's, we find our subcover, and then we map it back. That's how these proofs work over and over again.
Yeah.
Exact same thing we were doing over there. Feel like you got that one? Okay. Now our last one for the middle of the section, and we'll finish the section next time. I think we'll restart with this one next time as well, just to, I don't know. It's just what I was thinking when I was writing it. I'll decide next week, because I won't remember, so I won't promise anything. Anyways, let X be a topological space, and let D be compact in X. Okay, so D is some subset of X, and all we know is it's compact. Now, if C is a subset of D, and C is closed, then C is compact in X. In other words, once I have a compact set, then every closed subset of it is also compact.
That makes sense.
Okay. So, let's go through. Let D be compact, and let C be any subset of D that happens to be closed. Good?
Mm-hmm.
Let O be any open cover of C. Now, what am I looking for? I know that O is an open cover of C. I need to find a finite subset of O that still covers C. That's my goal. With me? So let O be any open cover of C. And note that C complement is open. How do I know that? Because C is closed. Okay. So O is an open cover of C. And C complement is everything that's not in C, right? So if I take C complement and I stick it inside of O, then O now for sure covers the whole set X. I know that O already covered C. This covers everything that's not C. So everything that's not C together with something that covers C covers everything. You with me?
Yeah.
Okay. So then O prime equal to O union C complement is an open cover of D. Because this covers everything. This covers all of X. So it for sure covers D, which is a subset of X. Now, since D is compact, then every open cover of D has a finite subcover. So, since D is compact, then there exists some S prime, S for subcover, then there exists some subcover of O prime, such that S prime is finite.
Say finite subcover.
Oh, there we go. I was going to say, I never referenced O prime. Such that S prime is a finite subcover of O prime, right? S prime is also a cover of C. Okay, yes. So, S prime is now a finite subcover of O prime. O prime covered D. So now S prime covers D. C is a subset of D. So now I know that S prime covers C.
Yeah.
Now, we do not know that S prime is a subset of O. We're looking for a subset of O that covers C. S prime is a subset of O prime. So it's possible that S prime has this element in there.
Yeah.
So we need to take that element out of there, and then we for sure have a subset of O. Okay, so right now I know that. So right now I know for sure that S1 covers C. Now notice, if I pull this element out of there, how much of C does this cover?
None.
None of it. So if S prime covers C, then if I take this element out of S prime, it still covers C. Does that make sense?
Yeah, it does.
Okay, so since C intersects C complement is empty, then S equal to S prime, removing C complement, is still a cover of C. Good?
Yeah.
And now S is a subset of O. And it's finite. So then S is a finite subcover of O. So C is compact.
Okay.
And once again, you see that exact same pattern. We started out with some open cover of one set, used it to get some open cover of another set, used that to get our finite subcover, S prime, and then use that to go back and get our initial subcover we were looking for, X. That's the pattern with these proofs over and over again. Which is why I told you that you sure need to understand what a cover is, an open cover, and a subcover. Because they never go away, and those are your tools for proving something is compact. So, we will continue with this next week. And probably do the section after it if you want to not read ahead.